Welcome to the series of talks on combinatorial optimization problem with special emphasis on pedigree polytopes and properties and consequences. We will be discussing an interesting property of pedigree polytopes. In this lecture, we will discuss the adjacency properties of pedigree polytope. Especially, we will discuss a non-adjacency testing problem for pedigrees. So I will first explain what is adjacency testing or non-adjacency testing in polytopes, and then going to discuss the non-adjacency testing problem in pedigree polytope. See, given a polytope, we have the vertices and then the edges, then the faces. These are all we saw in the preliminaries, or you already know when you discuss pedigrees. And we say two vertices of a polytope are adjacent if there is an edge connecting those two vertices. Two vertices are such that there is no edge connecting, but it is actually, you can say, a line joining those two goes through the polytope. Then in that case, that they are non-adjacent. Okay, so a simple way is to see that if two vertices are adjacent, then there is an edge connecting them. Otherwise, no. That means they are non-adjacent. So that's a simple definition. Another way to check this is if it is going through the polytope, then there is a midpoint of the two vertices, and that midpoint can be expressed with the help of other extreme points other than these two. In that case, they are non-adjacent. So this is actually gives you a formal definition how to check two vertices non-adjacent. Now these problems are interesting for various reasons. One reason is that the success in linear programming, simplex method for solving large problems, etc., initiated the interest in having algorithms which travel along the edges. So in simplex method, we start with one of the vertices or the corresponding basis, and then move to an adjacent vertex. So this movement is along the edge. So searching through the vertices to find the optimal can be done along the edges, and that was successful in the simplex-like methods. So the interest in trying to understand the adjacency structure of polytope became important. So let's look at one of the problem that is equally important. That's where the motivation I got for studying pedigrees is the traveling salesman polytope. So given the traveling salesman polytope, the tours are the vertices. Now given two tours, you may ask this question, are they non-adjacent? So if they are non-adjacent, you must produce an evidence that there are other tours such that you can express the midpoint of these tours as a convex combination of those other tours. So that's the idea. And this is an interesting question asked long time back by Papadimitrou. And he gave an interesting result showing that testing whether two tours are non-adjacent is as difficult as trying to find the optimal tour, or whether there exists a tour with less than or to given some value, etc., the decision problem there. So he showed that they are NP complete problem. That means this is also as difficult as that, as the set of difficult problem, which we know from complexity theory, the class of NP complete problem. So with respect to tours, we know adjacency testing is not easy. So naturally, our question should be, what about pedigrees? So when we discuss about pedigrees, now the vertices are pedigrees, and the convex hull of these pedigrees is what we call the pedigree polytope. I'm just repeating it again to make sure that you understand the polytope, what we are talking about, is clear. Now, given two pedigrees, whether they are non-adjacent, testing this can be our interesting question, because it's an equivalently important this one. So our problem is non-adjacency of pedigrees. Instances, number of cities is given, n is given, and you are given two pedigrees, x1 and x2. X super within square brackets 1 is one pedigree, x super square bracket 2, that is another pedigree. Both are in the same set of pedigrees, that is Pn. Question is, are x1, x2 non-adjacent vertices of convex Pn, that is the convex hull of these vertices? If the problem is clear, interesting, I think, of course, I can leave it to you to find out, but since I know there is that, it's very interesting to note that we can do this very easily, unlike what we saw in the case of twos. Okay, so that's I think that's why you should be interested in knowing the proof of that. Okay, actually, I should recall some history about non-adjacency testing in Turing polytopes. Kata G. Murthy, he gave a necessary and sufficient condition for two twos to be non-adjacent in the convex hull of twos. And you'll see the reference for that paper. T1 and T2 are non-adjacent if and only if there exists a T3 different from both T1 and T2, such that T3 is a subset of T1 and T2. That means the edges, subset of the edges. It is using only those edges. And if you take the edges which are common, T3 is actually covering all of them. That's the kind of this one. That is the intersection and union. That is the two things that he gave. But unfortunately, this result is not true. And MRO gave a counterexample for that. So that is about this non-adjacency with respect to twos. Now let's move on to studying the pedigree related one. So for this, for proving the results for this non-adjacency testing among pedigrees, I'll be using what are called fat problems. Because there is no need to go through this, but I'm doing it for a particular reason, because I'm going to use these fat problems in many places, and the proof becomes somewhat easy to see. So I'm using this, even though there could be other proofs in the literature. So what is a fat problem? So I need to talk about that before we can further discuss this. It is by itself is a very simple problem that we study in bipartite flow problem. Okay, so what is a bipartite flow problem? You will find many easy to find references for studying flows in networks. We will be using only the bipartite flow problem in this case when we are studying fat problem. But in the later sessions, we may also talk about finding flows in networks in general, which is not bipartite network. So it is good to have a good grasp of what is already known in flows in networks. And flows in networks, the early book, which is a classic, is then given by, written by Ford and Fulkerson. And that's a very interesting book, and that was the only book available when I was a student to know about this thing. But these days you have many updated, newer versions of newer results and newer versions of theorems, etc., in this area. And you can see the list of references given for them. And a bipartite flow problem has a set of origins, some say 1 to n, and a set of destinations. So you can imagine that, where you can, the source of certain things, availability, and where it is demanded, okay, so where it is used. So you have some availability in each of these origins, and you have some demand in each of these destinations. Now, from any origin, you may have routes to different destinations. It may not be all the destination, because some places it may not be possible to have roads or way to transport, so there may not be. So you have set of origins, set of destination, and each origin you have some availability, and each destination you need the same material, certain demand for that. Now, given the availabilities, let's call them A1, A2, etc., AN, and demands B1, B2, etc., Bm. So we are interested in finding out how to transport these materials to the destination with the least cost. If you are given the cost, that becomes a problem of minimizing the cost of transporting this from the origin to destination. A simpler problem would be just to see whether it is feasible to satisfy the demand from the available this one. That is what is the problem that we are interested in, feasibility of this one. And we are not so much interested in the cost, but they are related. We will see that later. So I call it FAT problem, even though I could have called it bipartite flow problem, is for a simple reason. The arcs in this bipartite network, these are coming from a certain logical reason, that is what we call certain arcs are forbidden. Okay, that means you cannot use them, forbidden. And this why they are forbidden, you have a logical reason for that. So they are called forbidden arc transportation problem. So instead of any transportation problem, you may have any two origin can be connected. And if you are solving with the cost, you can say if they are not connected, you can have a very high cost. That way you avoid that. So, but here we are interested in using this term FAT because forbidden arcs. Which arcs are forbidden? We have some logical reason for that. And this will be throughout this discussion, different reasons we may have for that, and we will know. So we understand what is a FAT problem. So just so finding the flow, the best maximal flow in this is what we are interested in. That is the feasibility, and then also doing the maximum possible flow. That's what we are trying to do. Not just, of course, this problem, I just skipped one thing, that is, this problem can be translated as a maximum flow problem in a bipartite network. So we can say they are equivalent problem. Okay, now we can define a FAT problem given these two pedigrees as follows. So we have, say, we are given two pedigrees, so you can consider them as two rows of information. Something like that. Now, there will be n minus 3 edges that we have selected, so the corresponding edges will be there for the first pedigree, corresponding edges will be there for the second pedigree. So this is kind of a table, you can imagine like that. So there will be a 1 if the particular edge is selected in that pedigree, otherwise 0. So you can compare the two pedigrees and see whether the same edge is selected in both, okay, or they are different. For each of the k, for k equal to 4, if I have used 1, 2 in the first pedigree and 1, 3 in the second pedigree, they are different because I mean using two different or two different common edges are there. But if they are same, then what we actually will, because they are, we don't have, because we know that it is the same, and that has an advantage in our algorithm, that noticing that. So they are quite a few definitions, but I will first explain the idea. It's very simple once you grasp this, but of course formally stating would require some mathematical definition. So imagine that because we know the pedigrees have this stem property, okay? So if you start at the last stage, nth stage, if you have two different edges in that, so if, let's say call them the edge in the first pedigree, say we call it say E1En, and so in the second pedigree, say let's call it E2n. If these two are different, what we will get a pedigree if by interchanging these two, if we do the following, that means the first portion of the first pedigree and the last n is E1n, the first portion of the second pedigree and then the last is E2n. Now if E2n has a generator in the first portion of the first pedigree, you know that this will also be a pedigree. And similarly, if the first portion of the second pedigree has a generator for E1n, then this also will be pedigree. So if both are satisfied, we can actually switch these two and you get two different pedigrees other than what we started with. So we will be able to now write the midpoint of the first two pedigrees as the midpoint of the third and fourth pedigree. So we are actually showing that they are non-adjacent. So it becomes simple. Actually that's the idea. But of course it may not be always like that. So if this is not the case, then something is preventing you from doing that. What is that? So there is no generator for this. So that is one reason why it is preventing. Or the same edge is used here because you should not have the same edge occurring again. So that is preventing. These are the two reasons it will be not possible. So then we say that it is welded to a particular number, we can say. So if it is at the fourth or fifth or sixth, whatever stage, we say that n is welded to that. Okay, that's the idea. So it is preventing you from doing that. Even if one of them is prevented, you cannot do that. Okay. So we go to the next one, n minus 1, and see whether we can do that. So if we can find a generator for, as I said, the previous portion, then you can do that, otherwise not. It's a very simple idea, but put it formally, we can give a simple routine for checking this, whether there is anything preventing you or not, etc. And this can be done in n power 3 order computation. So testing whether two pedigrees are non-adjacent can be done very efficiently, and the formal definition and the proof you will find in chapter 4 of the book. What we can do instead of going through the proof, I will take some examples so that you can check that your understanding of this algorithm is simple and clear. And actually one simple thing we can prove, if two pedigrees are differing in only one place, they must be adjacent, because there is no way you can get one from there, or if you do that, it is again the same pedigrees. It's not anything new, because if you interchange them, there is no, it is not new, because they are not two different pedigrees. You are just having the old pedigrees written in different order. So what we get, the first result is that if they differ in only one place, that means that we call that number of discards. So where they are discards, when they are not same. The number of discards is 1, then they are adjacent. That's a very simple result. We can easily verify that. For instance, this example, you are given P1, which is 1, 2, 1, 3, 2, 4, and 2, 6. So we have now, I'm only giving the discard and 4, 5, 6, 7. All the 4 edges where it is inserted, we have given for P1. That is 1, 2, 1, 3, 2, 4, and 2, 6. For P2, it is 1, 2, 1, 3, 2, 4, and 4, 6. Now, you see that 1, 2 is where 4 is inserted in both the pedigrees. That means it is same, so we can, that's not a discard. 1, 3, we are inserting 5 in both the pedigrees, we discard that. 2, 4, we insert 6 in both the pedigrees, we discard. So what we really have is only one place where they are different. So the number of discards is only 1. Okay, so we don't have to consider the other things because they are same. Now, since there is only one discard, we can conclude they are adjacent. Okay, so this is a very simple result, and it helps us to identify when they are adjacent. Okay, now after observing whatever I said, we have this simple procedure, find flexible, and this find flexible is used to check whether, if there is flexibility, that means you can actually get an evidence for non-adjacency. If it is not flexible throughout, then what happens is that we are able to show they are adjacent. That's the idea. So find flexible is a simple routine, and you can check easily that this routine is of a lower order polynomial. So using all these things, we have a major result that we are showing is that we can draw what is called graph of rigidity. Graph of rigidity, or GR. We can, whenever you, as I said, that welded to thing, you know n is welded to something else, or so you have two numbers corresponding to the discard, they are welded together. Now, if you take the places where there is discard, and those places, you can try to use those as the vertices, and then you can have edges between them whenever they are welded together. So then you get a graph. If that graph is a connected graph, then these two pedigrees are adjacent. Okay, so that is the result which we are proving. Of course, I'm skipping the proof of that, but the idea is very simple. This welded to idea is, and that you can intuitively see that what we are doing is right, and that's the proof. So if and only if kind of proof. So there is no, that means if that is not a connected one, then you have two components. Okay, otherwise there's only one component that's connected. When there are two components, you can take any one of the component and then swap the edges in that. Then you get two new pedigrees that become the evidence for your proof of non-adjacency. That's the idea. So let's take some example, and say here I am taking two pedigrees. First pedigree is 1, 2, 2, 4, 2, 3, 2, 6. The second pedigree is 1, 3, 2, 3, 2, 5, and 3, 4. Now, if you look at 1, 2, and then 1, 3, so there is a discard. 2, 4, 2, 3, there is a discard. At 5, at 6 also there is a discard because it's 2, 3, 2, 5. And last one corresponding to 7, it is 2, 6, 3, 4. So all these 4, 5, 6, 7 are the nodes for the graph because they are all having discards. Now we will start with the last, this one, that's 7. In the first pedigree, the edge we have corresponding 7 is 2, 6. And in the second pedigree, you can see that 6 is inserted between 2 and 6, so 2, 6 is available, so there is no problem. And 3, 4 is the last pedigree, last edge in P2, and 3, 4 is not available in 5. 3, 4 is not available because we are inserting 4 between 1 and 2. So we get only 1, 4 and 2, 4 and not 3, 4. So there is, you can't, it is not flexible at this point. So 7 and 4 are welded because the 7 is, there is something preventing it from being flexible, and that is 7 and 4 are welded. And then we go to 6. Then 6, what happens? 6 has got 2, 3 as the third edge, and in P2 the second edge is 2, 2, 3. So you can do, because that is preventing it from swapping or switching. So we are again saying 6 is welded to 5 because that's where this problem is happening. And we go to 5. Then 2, 4 is not available because the second pedigree has got 1, 3, so it has only 1, 4 and 3, 4 and not 2, 4. So 5 is actually welded to 4. So now you see the graph corresponding to this is actually 7 is welded to 4. There is an arc from 7 to 4, and then 6 to 5, and then 5 to 4. So now you see the whole thing is connected. 4, 5, 6, 7. They are all connected. So we have a connected graph. So these two predictions are adjacent. Okay. So that's the result we find. So you have some more examples discussed in chapter 4. So the main result, as I just want to recall, is that given xi belonging to Pn, I1, 2, consider the graph of rigidity gr. The given pedigrees are non-adjacent in convex Pn if and only if gr is not connected. So that's the result. So it's very easy to find out when the pedigrees are non-adjacent, and actually when the pedigrees are adjacent as well. This is a very interesting result. We can discuss other examples. I would rather give them as exercise to you to check whether they are adjacent or non-adjacent. So that concludes this module.